Welcome to week 9. This week we're going to continue our discussion of electrodynamics. We're going to continue talking about Faraday's law, induced EMF, and the flux rule, but we're going to look into these ideas all a little bit more deeply. This video is going to be a little bit different than our normal videos. I'm not going to have a lot of examples for me to show and for you to practice. We're really going to dig into something that I think is really interesting, and I hope you think it's interesting as well. Alright, so last week I mentioned a debate, so let's remind ourselves what that was. And if I wasn't quite clear about what that debate is, let me clarify it now. So this is definitely Faraday's law. This is what we were working with last week, where we could do this and there was no debate about whether this is Faraday's law. What the problem is that a lot of physics textbooks will pull this derivative outside of the integral. You should not do this. You can't just pull this derivative out of this integral. But a lot of books do. And they get away with it because the end result does end up being true. But mathematically, this is very much illegal because this is only about there being a time derivative on the magnetic field. Once you pull this derivative out, now you're saying that there could be a time derivative because the angle between B and dA changes, or there could be a time derivative because the path over which you're integrating is changing. So in general, you can't do this. If it is the specific case where it is just because of the magnetic field changing in time, sure, this is still true. But this is, as I understand the debate, this is where it comes from, is that too many textbooks claim this is true. And they change from the del's to the d's because this is magnetic flux, and magnetic flux only depends on time, whereas magnetic field depends on spatial coordinates and on time. Okay, so we looked at this last week. If you do this, you end up with the flux rule, where the minus the time derivative of magnetic flux gives you the EMF. So this is also where the issues of debate come up, is that if taking the time derivative outside of the integral was allowed, then yes, you could call this Faraday's law. But it's not allowed, so this is the flux rule. It's still true, it still works, but it's not Faraday's law. You may or may not care that much about what you call things. But it works, and that's what matters. And so last week we just focused on what happens when you change the magnetic field as a function of time. Okay, so let's back up and look at two of the experiments. So when we were doing Lenz's law last week, we were looking at how when you move a wire loop through a magnetic field, or the magnetic field changes with time, you get an induced EMF, and we were figuring out the direction of EMF. So we looked at a couple experiments. I want to look at those from a different perspective now. Alright, so we looked at these two situations. So let's call the one on the left experiment 1. So we have a magnet. The magnetic field is coming out of the screen, and then we have a wire loop. And we're moving the magnet to the left. This induces an EMF in the wire loop, so we get current flowing around the loop. We look at the experiment on the right. The wire loop is moving to the right, but the magnet with the magnetic field coming out of the screen is stationary. So when I look at these, I think initially these should give us the same result. In either case, we're moving the magnet or the wire loop so that less magnetic field is contained in the wire loop. It makes sense that we would get the same EMF induced in each case. So let's remind ourselves what we would expect. We're just thinking about Lenz's law. So there's magnetic field coming out of the screen, or the magnet is moving so that less of this magnetic flux is contained within the loop. So then the EMF is going to be induced so that the current that is induced can replace the magnetic field that is being lost. So it's going to induce an electric field coming out of the screen. So we want to curl our fingers around so that they come out inside of the loop that ends up with our thumb going counterclockwise. So in either case, we get the same EMF. Okay, so let's think about this in terms of Faraday's law versus the flux rule. So we can think about experiment number 1 as being Faraday's law, because if you just think about a given point in space, you could just pick a point, say right here. The magnet's moving away, so the magnetic field at this point in space is decreasing. So you still can say that the magnetic field is changing in time for a specific point in the space. So Faraday's law does apply. But for the situation on the right that we have in experiment number 2, the magnetic field is not changing in time. What we're doing is moving a wire loop. So Faraday's law should not apply. And I don't know about you, but this is very disconcerting to me. Well, it was when I first thought about it. So you have two situations that really seem like they should give you the same result, and they do give you the same result, but you have to use different laws to understand what's going on. Faraday's law applies to one, but not the other. Well, that's strange. So why is it that we get the same result in two situations that look similar, but the laws of electrodynamics do not apply to them in the same way? Okay, so before we go any further in resolving this, let's look at what is the proper way to understand what's going on in experiment number 2. Okay, and I'm not saying the flux rule doesn't work. The flux rule definitely works. What I'm saying is that we can't use Faraday's law to understand why it works. Okay, so how should we think about experiment number 2? Well, we should think about that one in terms of the Lorentz force law. So the Lorentz force law tells us that stationary charges can have a force on them because of an electric field, so this is the electrical force. And they tell us that moving charges can have a force on them that are a magnetic force from a magnetic field. And this one, the magnetic side, requires a right-hand rule. So in this rule, you put your thumb in the direction of the velocity. You put your fingers in the direction of the magnetic field, and then your palm pushes in the direction of the magnetic force. So we can use this to figure out how charges in that wire loop should be moving. To connect that back to EMF, we need to write this a little bit a different way. So we can write something called, well, it's little f. And that's the force per unit charge. Now, if something's purely electric, this is just the electric field. But it gets a little funny to call it electric field when you have V cross B in there. So we're just going to call it force per unit charge. Okay, so that's just the electric field plus V cross B. And we can calculate the EMF because EMF, which we have previously defined as the integral of the electric field around a loop, this is a little bit more general because it also includes the force from the magnetic field, is our force per unit charge integrated around a loop, or any length really. So it's very similar to when we're integrating an electric field around a loop, but now we have a force from magnetic fields as well. I want to make this all a little more concrete. I don't want to get too abstract. So we're going to use as our example to compare the results from the Lorentz force law to using the flux rule by using a situation that I know I learned in high school physics. I remember because my teacher had she had funny mnemonics for everything, so I remember lots of formulas from high school physics just because of the way my teacher talked about them. So if you cover these topics in your class, I bet this will look very familiar. But I want you to think about this more deeply, or perhaps just from a different perspective. So here's our situation we're going to work on. So we have this length of wire, and it has a resistor in it. And then we have a metal rod that's in contact with this wire, and it's sliding to the right with speed v. Then this is all happening in a region where the magnetic field is constant. It's coming out of the page, so B is in the z hat direction. And the length of the wire on this side is L. I've set my coordinate system over here, so z is coming out of the screen, and x is the direction of the velocity. Alright, so we're going to solve this problem two ways. We're looking to find the EMF induced in this wire loop with a special focus on what's happening in this rod. So the first way we're going to do it, we're going to use the Lorentz force law to solve this problem. After we do it that way, then we're going to use the flux rule to solve this problem. So this probably looks very familiar to a lot of you, but I know some of you haven't taught magnetism, so in which case this will look newer. Okay, so how do we find the EMF using the Lorentz force law? We have to find the force per unit charge in the rod, and then we need to calculate the EMF from that. Let's think about the forces on the charges first so we understand physically what's going on before we go ahead and do all our math. Okay, so part of our forces are electric, and that would come just from an electric field. But here's what we're looking at. We're looking at a wire and a rod that's full of positive and negative charges. Overall, there's really no electric force. Now let's think about the force from the magnetic field. Okay, so there's positive charges in the rod, there's negative charges in the rod. So let's think about what would happen to the positive charges. And remember, and maybe you haven't taught this, here's some new information. Current is defined for the direction positive charge moves. Okay, so we have positive charges in this rod. So we're going to put our thumb in the direction of the velocity. Put our fingers in the direction of the magnetic field, and then push with your palm down to show you the direction that the force is pushing. So positive charges are being pushed down in this metal rod. What's happening to negative charges? Negative charges, you actually use your left hand. So if I put my thumb in the direction of the velocity and my fingers in the direction of the magnetic field, then my palm ends up pushing up to show that negative charges are being pushed up. And this is in the rod because that's where things are moving. So EMF and current are defined in the direction of positive charge. So that means we end up with a clockwise EMF and clockwise current because that's the direction the forces are pushing the charges. If you want to reconcile this mathematically, what do we have? So we have little f, there is no electric field. And then we have V, so V is Vx hat crossed with Bz hat. And if you do cross product, you end up with minus Vb y hat. Okay, now we need to plug that into this. Okay, so the charges are only moving in the rod, so this only applies over the length of the rod. Now we could go through and do a formal line integral and say that dl equals dy y hat, and actually formally do this line integral. But we don't have to because this force is constant, so we don't really have to do an integral. All we have to do is multiply the force per unit charge times the length. Right, this is what this integral simplifies to. It's just f times L. So this is just minus VBL. But hold on, let's think about this. We're actually, normally when you go around loops, counterclockwise is the positive direction. We're going around in the clockwise direction, so that would be negative. So really there's another negative sign in here. So the sign can flip and you get VBL. Now I don't worry too much about signs when you're doing these because really you should be using lenses a lot to figure out the direction of your EMF. Trying to deal with signs in here, it's really easy to get confused, and it doesn't make conceptual sense to deal with the signs when you're doing integrals and cross products a lot of the time anyway. But if you do teach this subject, please let me know how you deal with the signs. Oh, and I really want to rearrange this BLV. This is because the mnemonic that my high school teacher taught me was that EMF is unbelievable. And then she would sing a song. You know that unbelievable song? Yeah. Okay, so here's our EMF. We have our answer. All right, and again, I'm not doing examples and then giving you ones to try because really what we're doing today is thinking about something more deeply. Because this is something that a lot of people teach with their students, and I want you to really understand it on a deep level. And it's really interesting. I think it's really interesting. I hope you agree. Okay, let's do this with the flex rule. All right, so here we have the same situation again, but now we're going to use the flex rule to solve it. All right, and so when we used the Lorentz force law, we looked at the direction of the forces on the charges inside the moving rod to figure out the direction of the current and the induced EMF. This one, we used Lenz's law to figure out the direction. So if we look at this, we have a magnetic field in the enclosed loop coming out of the screen. And the rod is moving to the right. The area enclosed by the loop is increasing. So that means the magnetic flux out of the page is increasing. Lenz's law says we want to resist that change, so the induced current should make the magnetic field go into the page. To make that happen, you want your fingers curling into the page inside the loop, which means that your thumb is pointing around the loop clockwise. So that tells you your EMF should go clockwise. That's the general wire right hand rule. It's actually easier if you just stick your thumb in the direction you want the magnetic field to go, then your fingers will curl around in the direction of the EMF. And I know at least one of you said that doing the right hand rule with this was confusing, so try that one. Stick your thumb in the direction you want the magnetic field to go, and your fingers will curl it around in the direction of the EMF. Okay, so to use the flux rule, we need to calculate our magnetic flux. In general, it's B dot dA, it's a surface integral, but the magnetic flux is constant, but the magnetic field is constant in space, so that means it's just B times the area. So if you do B times the area, it's B. One side of the loop is L, the other side is X. Okay, why can I do that? Well, I set my coordinate system over here. I wrote this down without saying anything about it. I set this side of the loop to be x equals 0, and this side is x. It's the variable. I just defined it that way to make the math simpler. Now, actually, this comes out negative. I won't worry about it too much, but because your magnetic field is coming out of the page, but your EMF is going clockwise, so your dA really should be defined into the screen. So because those are opposite directions in and out of the screen, this actually has a minus sign. But don't really worry about it. Lenz's law tells you directions, so it's not that big a deal. Alright, so now we just need to take the time derivative of this. Well, negative the time derivative. Okay, I'm going to pull out our constants. Minus signs cancel. Okay, now we talk about this next part in classical mechanics, and we talk about it in math methods. So it so happens that the time derivative of position is velocity. And any of you teaching calculus-based physics would know this, but I bet it's new information to somebody. So what I'm doing here is using the definition. Because you know that the change in position over the change in time gives you velocity. Derivatives are basically the same thing. So we get BLV. Oh, it's the same result we got last time. Well, that's good. Okay, so you can use the Lorentz force law, and you can use the flux rule and get the same answer. That's kind of cool. That's also kind of weird. Okay, so we can solve this problem two different ways. Why is that? Go back to thinking about our first two experiments. Let's go look at them. Okay, so we are looking at this one. So on the left, we have the magnet is moving, so the magnetic field is changing in time for a specific point in space. So Faraday's law applies, we get an EMF. The situation on the right, The magnetic field is not changing in time, we're just moving a wire loop. Faraday's law does not apply. Same thing happens. What's going on? And how can we explain both using Maxwell's equations? Well, the fact of the matter is, this all comes down to relativity. So Newtonian mechanics is not consistent with relativity. It's a simplified case, but electrodynamics is consistent with relativity. Let me mention something else to you that maybe will help you think about this a little bit more. So think about, from the Lorentz force law, what the magnetic force is. This tells us that the force on a charge depends on how fast it is going. But that can get disconcerting if you start thinking about it too hard. Okay, so something we do in mechanics is you can say, all right, I'm in the reference frame where I see that boat drifting down the river. It's going some velocity. But then you could put yourself in another reference frame where you say, all right, I'm in the boat. I'm going to imagine the boat has no velocity and the river is what's moving. The riverbanks are what's moving by me. So you can change your reference frame and it doesn't really change what's going on. But if you change your reference frame in electricity and magnetism, well, now your magnetic force depends on what has velocity. So say you have an electron traveling along. You're a bystander, you're watching the electron with some velocity. You're going to say, all right, there's going to be some magnetic force on that electron if there's a magnetic field in the area. But if you put yourself in the reference frame of that electron, where the electron is at rest, then you don't think there should be a magnetic force on that electron. That is what's weird about electrodynamics. It comes down to relativity. Let's think about this some more. So here's the thing. We're thinking about this electron that's moving in an electric field. We can change our reference frames. We can put ourselves in the reference frame where the electron's at rest. When the electron's at rest, there's still going to be a force on it. Turns out it's an electric force. But if we're in a different reference frame and we're watching that electron go by, then there's a magnetic force on it. So you can have the same situation, like situation 1 and 2 here are the same situation. Really, it's the same situation in different reference frames. In the first one, the wire loop is what's at rest. In the second situation, the magnet is what's at rest. And so in the first situation, we're using Faraday's law to find the electric field that's induced. So in the first one, it's an electric field that is making the charges move around. In the second one, it's the magnet that's at rest, and now it's a magnetic force making the EMF appear. This is really interesting. This is really weird. I just have trouble thinking about relativity. I don't know about you, but it kind of blows my mind every time. So, no matter what your reference frame, you get the same results. But depending on your reference frame, you can have purely electric forces, purely magnetic forces, or a mix of electric and magnetic forces. But no matter what your reference frame, in the end, the same thing happens. Tell me what you think about that. And again, these are all fairly simple examples that you can do in your classes, but I want you to really understand them on a deeper level. And I, for one, had always heard that electric and magnetic fields were the same thing, something with relativity, and I didn't quite get it because my classes never ran long enough, so we can't go into it in full mathematical time. I'd have to spend a couple weeks going over relativity before we could do it. But it really does come down to, depending on which reference frame you are in, which object you're considering at rest, your forces can switch between being electric and magnetic forces. Okay, this is a little different than our normal videos. I hope you found it interesting. Well, next week we're going to look at Ohm's law, and it's going to look a little bit different than what you may be used to. Okay, well, let me know if you have any questions. Let me know what you think about relativity and what it has to do with electric and magnetic fields. I look forward to hearing from you, and I'll see you later.